People keep asking, when will AI become smarter than humans? But there is a more important question. No matter how intelligent AI becomes, are there things it will never be able to know for certain? The answer is yes. Not because it lacks data, not because it lacks chips, not because the model is not big enough, but because back in 1936, Alan Turing proved that every computational system has limits it cannot cross. That may sound abstract, but you have already seen this limit many times. When you install software, your computer may say, 2 minutes remaining. Then suddenly, 17 minutes remaining. Then it freezes at 99%. If a computer cannot always predict exactly when a simple task will finish, why do we assume AGI will be able to predict, verify, and solve every complex problem in the world? This video is not saying AI is useless. In fact, AI will be extremely powerful, but it will never be all-powerful. And the reason begins with Alan Turing's most famous proof. In 1936, Alan Turing asked a question that seemed harmless, but ended up revealing a fundamental limit of all computers. Can we create a program that can always predict whether another program will eventually stop or run forever? To make this easier to understand, imagine such a program exists. Let's call it HALT. HALT reads the source code of any program and answers, it will stop. Or, it will run forever. That sounds reasonable. If we already have the entire source code, why shouldn't we be able to predict what it will do? But then Turing introduces a second program. Let's call it Rebel. Rebel has only one job, to do the opposite of whatever HALT predicts. If HALT says Rebel will stop, Rebel runs forever. If HALT says Rebel will run forever, Rebel stops immediately. Now let Rebel analyze itself. In other words, Rebel gives its own source code to HALT and asks, will Rebel stop or will it run forever? But Rebel is designed to do the opposite of HALT's answer. If HALT says Rebel will stop, Rebel does not stop. If HALT says Rebel will not stop, Rebel stops. In other words, no matter what HALT answers, HALT is wrong. So a perfect prediction program like HALT cannot exist. This is the halting problem. It proves that there is no general algorithm that can always predict whether every possible program will eventually stop or run forever. And here is the most important point. This limit does not come from weak hardware, missing data, or a lack of GPS. It is a mathematical limit. It is a wall built directly into the logic of computation itself. Now let's return to AI. Many people imagine AGI as an intelligence that can do everything. Write code, conduct scientific research, run companies, invent new drugs, optimize the economy, maybe even upgrade itself. But there is one truth people often overlook. No matter how powerful AI becomes, it is still a computational system. It receives data, processes information, and produces outputs. That means it cannot stand outside the limits Turing identified. Imagine an AI is given a problem no one has ever solved before, a mathematical theorem, an extremely difficult software bug, or a completely new scientific question. The problem is that AI cannot always know in advance whether that problem has a solution. If it stops too early, it may miss the answer. If it keeps going forever, it may get trapped inside a problem that has no solution. So every AI system must have stopping points: time, tokens, compute, energy. At some point, it has to give the best answer it can within its current limits. And that reveals something important. AI cannot guarantee that it is always right. It can only optimize within the resources available to it. So the idea of an all-powerful AGI that always solves every problem correctly, in finite time, is not just difficult to build, it runs directly into a foundational limit of mathematics. The deepest part of Turing's proof is not just about whether a program stops or runs forever, it is about what happens when a system starts looking at itself. This is called self-reference. The most famous example is the sentence, "This sentence is false." If the sentence is true, then it becomes false. If it is false, then it becomes true. It sounds like wordplay, but it points to a serious logical problem. When a system is powerful enough to talk about itself, it can create loops with no clean way out. With computers, this problem becomes even clearer. A program is not only something that runs, it can also become data, something that can be read, analyzed, and even analyzed by itself. At that point, a program can look at its own source code, predict its own behavior, and then change its behavior based on that prediction. And if it can react to the prediction, it can also make the prediction wrong. This is why the idea of an AI that can perfectly understand itself, perfectly audit itself, and perfectly fix itself sounds attractive. But it cannot be guaranteed in every case. AI can improve itself within narrow domains, especially when the goal is clear and the results are measurable. But with a general system operating across many contexts and many different goals, the question becomes much harder. How can it know for certain that every self-modification actually makes it better? There is no general guarantee for that. So self-reflection may be a sign of intelligence, but it is also where intelligence runs into its own limits. AI cannot always predict whether a program will stop or run forever, but you might think, fine, then let's just check whether the AI is safe. The problem is that even this cannot be guaranteed absolutely. In 1951, Henry Gordon Rice proved a result even broader than the halting problem. For any sufficiently complex program, there is no general algorithm that can always verify its entire behavior perfectly. Put more simply, we cannot always prove with certainty that an AI will always be correct, never cause errors, never do something dangerous, always be honest, always remain aligned with human goals. This strikes directly at a common idea in AI safety. If an AI becomes too powerful, we can build another AI to supervise it. But then the next question appears, who supervises the supervising AI? If we create yet another system to check that one, we have only moved the problem one level higher. Eventually, we still need some system we trust to always be correct. And Rice's theorem tells us that for general systems, that absolute guarantee does not exist. There is no overseer that can inspect every AI and prove that it will always be safe, correct, fair, and honest in every possible situation. This does not make AI safety meaningless. It just forces us to be more realistic. The goal is not to reduce risk to zero. The goal is risk management, better testing, continuous monitoring, red teaming, formal verification in narrow domains, human oversight, and intervention mechanisms when systems fail. With AI, the right question is not, how do we guarantee it will never fail? The right question is, when it fails, how do we detect it early, limit the damage, and keep humans able to intervene? This is why AI creates such an uncomfortable paradox. It can be extremely intelligent and still be confidently wrong. It can write an answer that sounds persuasive, while the facts are fabricated. It can beat benchmarks, then make basic mistakes in the real world. It can help programmers move incredibly fast, while sometimes generating bugs that take humans hours to fix. Many people think, just add more data, add more compute, train bigger models. Eventually, these errors will disappear. But it is not that simple. Data makes AI better, compute makes AI stronger, but neither turns AI into an absolute source of truth. Machine learning does not learn truth in a perfect sense. It learns patterns, correlations, and probabilities from data. When a new situation resembles what it has seen before, AI can be highly accurate, but when it encounters an edge case, an unfamiliar context, or a changing environment, there is no guarantee that old patterns still apply. So we should understand AI for what it is, a very powerful, probabilistic system within the right domain, but not something that can be trusted absolutely in every situation. In simple terms, AI is an amplifier of human ability. It is not an oracle. Even when a problem does have a solution, AI can still run into a very practical barrier, the cost of finding that solution. A classic example is the traveling salesman problem. A salesperson has to visit many cities and return to the starting point. The question is simple: what is the shortest possible route? With only a few cities, the problem is easy. But as the number of cities grows, the number of possible routes does not grow slowly. It explodes exponentially. This is called combinatorial explosion. And the real world is far more complicated than that. Economies, traffic systems, social networks, financial markets, or an AI interacting with users, the internet, code, and a long list of tools. There are too many variables to examine every possibility, so every finite intelligence, human or artificial, has to do the same thing: simplify the problem. Estimate, ignore some branches, use heuristics, accept answers that are good enough. This is not a flaw unique to AI. It is the price of thinking in a world limited by time, energy, and resources. A perfect answer that takes 1,000,000 years to compute is useless in practice. So the real question is not only, can this problem be solved? The real question is, can we find a good enough solution, fast enough, at an acceptable cost? From all these limits, one principle becomes very important. The more things AI tries to do, the harder it becomes to trust absolutely. A specialized AI can be extremely powerful because its problem is clearly defined. A chess AI is strong because the rules are fixed and the goal is simple: win the game. A medical imaging AI can be effective when the data and context are tightly controlled. But an AI that does everything is different. When it has to write, program, analyze law, give strategic advice, understand emotions, or make ethical decisions, it enters a world that is much more ambiguous, variable, and difficult to verify. It becomes more flexible, but it also becomes less certain. This is the spirit of the no free lunch theorem. There is no algorithm that is best for every problem. Every algorithm is powerful because it matches certain assumptions. When those assumptions are correct, it works very well. When the context changes, those same assumptions can become weaknesses. So the future of AI is probably not one machine god that does everything perfectly. A more realistic future is an ecosystem of specialized AI tools, each powerful within its own domain, coordinated, verified, and applied by humans in the right places. This brings us to the biggest question about work. If AI is not all-powerful, what value do humans still have? The answer is, humans do not disappear. The human role shifts from doing everything directly to evaluating, coordinating, and taking final responsibility. AI will help us write faster, code faster, research faster, analyze data faster. But when AI can generate hundreds of options in seconds, the advantage is no longer who can produce more. The advantage belongs to the person who knows how to choose well, who knows which option is trustworthy, which answer needs verification. When AI is operating beyond its limits, which tasks should be delegated to AI, and which decisions must remain human. In the AI economy, the most important skill is not just knowing how to prompt, it is taste, the ability to judge, filter, and make decisions among a flood of AI-generated possibilities. The winner is not the person who outsources all thinking to AI. The winner is the person who uses AI to amplify their abilities while staying clear-headed enough to verify, coordinate, and take responsibility. In 1936, Alan Turing did more than lay the foundation for computer science. He left behind a warning that becomes even more important in the age of AI. Not every limit disappears when machines become more intelligent. Some questions have no general method of solution. Some systems cannot perfectly verify themselves. Some risks cannot be reduced to zero. And some problems cannot be solved simply by adding more data, more compute, or more parameters. AI can be extraordinarily powerful. It can amplify human ability at a scale we have never seen before. But AI is not magic. It is still bound by logic, computation, and the limits Turing revealed. So the lesson is not that AI is useless. The lesson is this: the more powerful AI becomes, the more humans need to understand its limits. Only by understanding those limits can we know what should be automated, what must be verified, and what should never be fully handed over to machines. In the age of AI, real intelligence is not believing that machines can do everything. Real intelligence is knowing where to use AI, how much to trust it, and when humans must take final responsibility. If you want to understand AI not just through hype and promises, but through the fundamental limits of mathematics, technology, and economics, subscribe to the channel. In the next video, we will continue with an even more important question. If AI cannot perfectly verify itself, how should humans verify AI?